the third lecture we shall talk of network equations and initial and final conditions. In this course we will assume that you know KCL, KVL, Ohm's law of course, and we also presume you know Laplace transforms and Fourier transforms. Am I justified in assuming this? Yeah, okay. So there are basically there are two ways of writing network equations. Given a network N, you can solve it by writing one of two sets of equations. First set is based on what is called a mesh basis. Network equations, network analysis can be based on mesh, identification of meshes and writing mesh equations, or you can write node equations. You have written mesh and node equations in the previous course also. Here we shall be a little more general, that is we shall include initial conditions and see how things differ. Basically this will also be a little bit of review of what you have done earlier, but let me point out some of the basic foundations of mesh analysis and node analysis. There is also a term loop equations. There is also a term loop instead of mesh sometimes used, and you must be able to distinguish between a loop and a mesh. A mesh is the smallest size closed path which does not contain any other closed path inside this. Okay, a mesh is the smallest size closed path which does not contain any other closed path inside it. For example, if we have a network like this, I have simply drawn in terms of lines. Each line, each part of the line may represent an element. This may be a resistance, this may be a source, and so on and so forth. This is called a graph of the network, where every branch is replaced by a line. Now you see, if this is the network graph, then this qualifies for a mesh. Okay, but this does not qualify for a mesh. The colored one, the pink colored one, is not a mesh, it is a loop. The pink colored one is a closed path. It contains another closed path, the green colored one, inside this. So this is not a mesh, this is a loop. On the other hand, this is a mesh. A mesh is a loop, but a loop is not necessarily a mesh. Is that okay? Both are closed paths, both are circuits. One can contain another circuit inside, the other cannot. And therefore all meshes are loops, but all loops are not meshes. I'm sorry. The coat is thick. Okay. All loops are not necessarily meshes, but all meshes are loops. Now the number of equations that has to be written, that is a very important factor, and the number of mesh equations, is given by the number of branches B. The number of mesh equations is given by the number of branches B minus the number of nodes N plus 1. This is the number of mesh equations that have to be written. this is a set of independent mesh equations that have to be written in order to be able to solve the circuit. On the other hand, in node equations, the number of node equations is simply equal to the number of nodes minus 1, that is it. Whereas, the number of independent mesh equations involves the number of branches, the number of independent node equations does not involve the number of branches. And in a given situation, for a given network, one of them will be advantageous as compared to the other. Naturally, if you can do with writing only one equation, why should you write two? If the number of mesh equations required is 2 and the number of node equations required is 1, naturally you shall prefer node basis analysis, and this is what determines in a given situation whether you shall be using mesh analysis or node analysis. There are many situations in which the number is the same, then it depends on your personal prejudice, personal preference, there is nothing to choose between. And this we shall illustrate by two examples, one of mesh analysis and the other of node analysis. The example that I take is 5.1 from the textbook Kuo, and the network is given like this. There is a voltage source ET UT plus minus, then there is a inductor L which carries an initial current IL 0 minus. As you know, the initial conditions are now to be, instead of 0 it would be 0 minus, because we have to distinguish between 0 minus and 0 plus because of the possibility of occurrence of an impulse function or its derivative. Okay. The next element is a capacitor C1, and the voltage across this is denoted by this polarity, and the initial voltage is Vc1 0 minus, this is the initial voltage. Then a resistance R1, a capacitance C2 with this polarity of voltage, and the initial voltage across this is Vc2 0 minus. And then we have another inductor L2 in which the initial current is IL2 of 0 minus and a resistance R sub 2. This is the network. This is a two mesh network. Okay? Two meshes are required. Two mesh equations shall be required, and you can identify, you can say the first mesh equation is I1, we introduce a circulating current, a hypothetical circulating current, and the second mesh equation contains the current I2, circulatory current I2. How many loops can you form in this? 3, alright, 2 meshes and 1 big loop, okay, 2 smaller loops and 1 big loop. Now if you describe this in terms of a graph, network graph, it depends on what nodes do you identify. Okay. Obviously this network requires 2 mesh equations, 2 independent mesh equations. There is one more point that I want to mention about mesh equations, is that if you have written a set of mesh equations, then each element of the network must be at least in one mesh, otherwise you have not written it correctly. Is that clear? Each element of the network must form part of at least one mesh, if not more. For example, these 2 elements R1 and C2, they are in 2 meshes, but L and C1 are in mesh number 1. Now you can also see that if you want to write node equations for this circuit, the only node equation that you have to write only one. You see, this is the only voltage that is unknown, V. If you can solve for this voltage, then you know the currents in all the branches, you know the voltages across each element, and therefore a node equation is to be preferred in this situation, alright. But let us write the mesh equations and let us see how to write the mesh equations. A certain discipline has to be followed in writing mesh equations and node equations, alright. The discipline that I follow, you may or may not like it, you may follow your own discipline, but the discipline that I follow is I identify the source in the mesh. The source, obviously the only source is ET UT. All others there are three other sources in this. One is for the inductor initial current, one is for the capacitor initial voltage, and the third is for the second capacitor initial voltage. These three, as you know, act as sources. The inductor current acts as a current source, the capacitor initial voltage acts as a voltage source. Similarly, here also there is a voltage source, but we shall take care of them while writing the equations. We first find the driving energy source. The driving energy source is ET UT. So, we write ET UT is equal to then we write the drops across the elements. The first one, the inductor, obviously the drop is L dI1 dt. The current across this is current through this is I1. The initial current IL 0 minus does not specifically enter into this equation because it is a differential coefficient, plus the voltage drop across C1 shall be due to the current I1 and due to the initial voltage. So, it would be 1 by C1 integral 0 minus to T I1 tau d tau plus V C1 0 minus. This is the voltage drop across the capacitor C1. In writing this equation, you must be cautious, you must be careful about the polarities. That is, the flow of current I1, does it produce a voltage which is in agreement with the polarity of the initial voltage? If they are, then the sign is plus. If they are not, then you have to make one of them a negative sign. Okay. Then plus the voltage drop across R1 shall be R1 times I1 minus I2, because that is the current in this. Okay. The current is I1 here and the second mesh current goes up. So, it is I1 minus I2 plus the drop across C2, which for similar reasons is 1 by C2 0 minus to T. Now, the current that goes into C2 is for this polarity is I1 minus I2, and therefore, it would be I1 tau minus I2 tau d tau, all right, plus or minus I1 minus I2 agrees with Vc2. So, it would be Vc2 0 minus. This is the equation for mesh number 1. Now, for solving such an equation, we shall write the second equation later, but for solving such an equation, the terms which are sources, Vc1 0 is like, it is independent of time, it is a constant, it acts as a source, you transfer it to the left, that is minus Vc1 0 minus, then you cancel this, and the term Vc2 0 minus you also take it to the left hand side, so that on the right hand side remain only differential coefficients or integrals, all right. All initial condition terms are transferred to the left, and the effective source for this mesh would be the combination of these three terms, that is the driving force, the driving source, energy source, and the two sources due to initial conditions. Yes. Because this is a function of time. Okay. These are dependent variables, independent being tau, all right. We do not know them. So, we keep all the unknown quantities on the right hand side, all known quantities on the left hand side. This is another way of looking at it, alright, because we have to, what we have to do is to solve for I1 and I2. Unfortunately, this is not an equation containing I1 only, it also contains I2, alright, and therefore we must write the second equation to be able to solve for the network. And the second equation would be like this. There are no energy sources in this, so I write simply 0 and I follow the direction of I2. Let us start from here, L2, then it becomes L2 di2 dt, the initial condition does not matter, plus R2 multiplied by I2, this is the only current that flows in R2. Then comes the question of C2. You see C2, if you write 1 plus 1 by C2 integral 0 minus to t I2t minus I1 tau d tau, then the initial condition term now should come with a negative sign. So, minus Vc2 0 minus, okay, then plus R1 multiplied by I2 tau minus I1 tau. This is the set of mesh equations. And you see here also you can transfer the time independent term or the initial condition term to the left hand side, then you get Vc2 0 minus, okay. This is a discipline that I follow and I find it very convenient. That is, on the right hand side you keep only the unknown quantities expressed in terms of differential coefficients or linear terms, I2 is a linear term, or integral terms, but the common link between them is that each quantity is time dependent. On the left hand side are the known quantities. Known quantities can be time dependent or time independent, it does not matter. Time dependent example is the driving force ET UT, alright. And what you have to do is to solve for these two equations. You can solve either in the time domain or in the frequency domain, okay. You have to, in the frequency domain you have to take the Laplace transform of the two equations, then you know that differential equations or integral differential equations simply become algebraic equations and you can solve for them. We shall not continue. Okay, why was it I2 minus I1? Because we are going in this. Oh, why not T? Is that the question?
In the second one, sir, in the R1E2.
Oh, I have to write T. Thank you very much. It would be I2t minus I1t. I made a mistake. Tau is a dummy variable in the integral. It cannot be. It is a function of time here. Thank you. We don't we don't go ahead with the solution of this because we are illustrating only the writing of mesh equations and node equations. Now I must also point out there is nothing sacred about going clockwise. You could also go anti-clockwise. For example, in the choice of the mesh equations, we could go like this. We could have identified I1 in the other direction. Well, this is convenient because ET UT tries to send a current in this direction, in the direction of I1. That is why we chose it. It is purely a matter of convenience. As long as you are careful about your credits and debits, positive and negative sign, you are perfectly stable with regard to your economic condition. If you know how much, what is your positive side and what is your negative side. Okay, that is all that you have to know to write mesh equation. So you know you have to have Ohm's law and KVL and a certain amount of discipline and a certain amount of caution with regard to signs of the initial conditions. Let us take an example of a node equation, and this example is 5.2 in Kuo. And this example is like this. We have a current source IT UT, and unit a step current source IT UT, then you have a resistance R0 which possibly could be the internal resistance of the current source. Okay, it could be a non-ideal source. R0 could represent the internal resistance of the current source. Okay, then you have a capacitor C1 C0 whose initial voltage is Vc0 0 minus, okay. Initial voltage is Vc0 0 minus with this polarity plus minus. Then you have, to complicate matters, a resistance R1, an inductance L whose initial current is IL 0 minus, then a capacitor C1 whose initial voltage is Vc1 0 minus. The polarities must be given, which polarity it was initially charged to, and then these two come together and we have a resistance R2. We have to write node equations for this. Obviously, the nodes whose voltages are not known are this node, call this V1, this node, call this V2, and in addition you require a node here, let us say V3. These are the three unknown voltages that have to be determined in order that you can determine the currents and voltages in all parts of the network, okay. And we proceed in the same disciplinary manner as we had done earlier, that is, we write node equations for node 1, node 2 and node 3 by identifying the driving source. For node 1 the driving source is ITUT, so you write ITUT is equal to
So what is the requirement of V3?
Because there are two elements with two initial conditions. Unless you know this voltage, you cannot write the equation for C1, you cannot write the equation for L, alright. You see the current through this would be L d V1 minus V3 dt. That is why we have to take the node V3. If initial conditions were absent, if there was no initial condition, then you could simply take Laplace transform circuit, and then this could be treated as one branch. It is because of initial conditions that we have to identify a third node here, okay. So we are saying the current arriving at the node 1, which is driving force ITUT, that must be equal to the current leaving R0, which is V1 by R0, plus the current leaving C0, this must be C0 d V1 dt. The initial condition does not show explicitly here because it is a differential coefficient, plus the current that leaves R1, which is obviously V1 minus V2 divided by R1, alright. Then the current that leaves L, this is 1 over L integral 0 minus to t, alright, the voltage, that is V1 tau minus V3 tau d tau, okay. This is the current, and then the initial current plus, is it plus or minus? Plus, because it agrees with the current leaving, so it would be I L 0 minus. This is the node equation for node number 1, alright. And we can obey the same discipline, namely we can transfer this term, the initial condition term, to the left hand side, and we can write minus IL of 0 minus. Then on the left hand side are only known quantities, on the right hand side only unknown quantities, alright. Let us go ahead with the completion of this example. We next write the node equation for V3. For V3, you see there are only two currents to be taken care of, that is the current through C1 and the current through L, alright. So what we have is this situation L and C3, this node voltage is V2, this node voltage is V1 and this is V3. So the node equation would be 1 by L, the current going from V3 to V1, okay. Which way should we do? What I am going to do is that this, there is no driving source, and therefore this current plus this current must be equal to 0. This is what I am going to write. So 1 by L integral 0 minus to t. Now notice the polarity, V3 tau minus V1 tau, this is the current leaving V3 d tau, then minus IL of 0 minus plus C3 the capacitor, then d V3 minus V2 dt. This should be equal to 0. This is the equation for node 3 V3. Is this clear? The polarity. Now what you can do is you can transfer this quantity to the right hand side, and then you have the same discipline, that is one side of the equation contains unknowns, the other side contains knowns. Okay.
So doesn't the initial flowing of IL 0 minus through inductor implies the current flowing through a capacitor also?
That was at 0 minus. At 0 minus, the inductor might have had another path, okay, which was open at t equal to 0. It is possible to establish a current in the inductor. See, at t equal to 0 minus, perhaps there was a current source here which has established a current IL 0 minus, and then at t equal to 0 this is taken off. Okay. So it is possible. Now the last equation, the last node, that is V2 node this node has the following components. You see, V2 by R2 is the current leaving through R2 plus V2 minus V1 divided by R1 is the current leaving through R1, and plus C1 d V2 minus V3 dt. Okay. These are the three currents. The current through R2 is V2 by R2, the current through R1 is V2 minus V1 by R1, and the current through C1, that would be C1 d dt of V2 minus V3. Okay. So the sum of these three currents equal to 0, and there are no known quantities on this side, and therefore there is nothing to transfer. Also note that the initial condition of the capacitor does not arise anywhere, and the reason is that the capacitor, we are writing equations in terms of currents, and currents are differential coefficients of voltages as far as capacitors are concerned. So that takes care of an example of a node equation, and we used an example from the textbook Kuo. Yeah.
So for this circuit, can we write mesh equations also?
Of course we can write mesh equations.
Sir, but what if you call the case that if we are taking for the second part of the circuit between C0 and R2 to take this in a particular mesh, then it would be, there would be one more smaller circuit in that mesh.
We'll take one particular.
No, what we will do is if we want to do a mesh equation, what we will do is, this is one mesh. Let me use another color. This will do. This is one mesh. This is one mesh. This is one mesh, and this is one mesh. 4 mesh equations here. However, things are not that bad, because this current IT ut is known. So the first mesh equation is known, alright. Second mesh equation is unknown, third is unknown, fourth is unknown. So you have to solve for 3 mesh currents, and since only 2 node equations, no, how many node equations did we write? 3. So there is nothing much to choose, they are identical. In the previous example,
Can you have a mesh passing through R1 also?
can you have a mesh passing through R1?
R1 and then
No, we cannot, because then this will be inside. That is not a mesh. This is C0, R1, R2. This is a loop.
We can interchange the positions of R1, L,
and C.
Okay, okay, agreed. That means you interchange R1 and L because they are in parallel. Yes, we can do that. But as drawn here, it's a planar structure. Depends on the way you look at it. all right. If you interchange the two, yes.
Again,
It's a
in
loop
case
or
of
mesh.
Pardon me? If you interchange these two, then through R1 it would be a mesh.
Otherwise it would be a loop.
Otherwise it would be a loop, yeah. As we have written,
So as you
yes.
said, there will be two known quantities. In case of mesh 1, there will be one quantity. So we can change R0 and C0,
We can.
and we can get one more known quantity.
Agreed?
And then
No. See,
because there
the choice of meshes is unique. Once you have chosen this, no question of interchange. No interchange, no. Once you have chosen the structure and the meshes, period. You can't be in two minds, no. It might work in life, but not in circuit theory. Okay?
So
Yeah.
where do you have the fourth node?
Where do you have the fourth node? Fourth node is here, the ground node, which is taken as zero potential. You see, whenever you say this voltage is V1, we mean that we have a reference. And this is why the number of independent node equations is equal to number of nodes minus 1. That minus 1 comes because of the reference node.
So what is the requirement of the second mesh?
What is the requirement of the second? This mesh.
Yes, sir. So we have already included the two components.
Oh, but it's not the other way around. You see, every component must be in at least one mesh. It is not necessary that only one mesh should contain one component. No, the other way is not true. So a component may occur in 2, 3, 4 meshes.
So that means three mesh won't solve the equation.
3 mesh would solve because one of them is known. This IT, UT is known, and therefore 3 independent equations. Agree? That happens because this source is known, not otherwise.
So what is meant by branches in that equation we have written n minus b plus 1?
Oh, branches means any two terminal element is a branch. One, this is a branch, this is a branch, this is a branch. This consists of two branches connected together here. Okay. So a branch is, if we draw the skeleton of the network, for example, the skeleton of 5.2 would be like this. This is the graph of the network, and the number of branches is 1, 2, 3, 4, 5, 6, 7, 8. This is not a branch because this is a zero potential. This is a short set.
But there is in the two parallel
One at a time. Yeah, two parallel
yes,
components.
The second one,
Yeah.
they have two components.
Yeah, you can consider this as one component. Is that what?
That is what I am asking, that in that parallel connection, in the second part we have two components. So we will consider that as two branches or one branch.
It doesn't matter what you consider. Depending on that, you have to write the required number of node equations. As you see, this series connection could be considered as one component. But because of inductor and capacitor and because of initial conditions, we cannot take care of the initial conditions by considering as one component. And therefore, we consider these as two branches. Because this voltage is to be determined.
So we have to add one more node also.
Yeah. That will be obvious in the context. For example, if we had two resistances in series, then we would not have put a branch here.
So, but in the skeleton diagram, you just made one branch.
I just made one branch, okay, I made a mistake. Two branches. Alright? You should know how to take care of teacher's mistake. Okay? And it's mutual. This microphone today is. Now it will be all right. Okay. Now once you have been able to write the equations, the next task is to solve them. And once you have written the equations, the next task is to solve them. Now solution of an equation, differential equation, requires initial conditions. And as I told you, initial conditions are conditions at t equal to 0 plus, not at 0 minus. For solving a set of differential equations, the initial conditions would have to be evaluated at t equal to 0 plus. And this can be done in two ways, either from physical considerations or from the differential equation itself. Alright. and we shall look at how to find out initial conditions through a couple of examples again. But let me tell you that the solution is that of a voltage or a current always contains two parts. One is the complementary function Cf and the other is the particular integral Pi. The complementary function, as you know, is called the free response or natural response. You are acquainted with these terms? Yes. Free and forced? Okay. It is either free response or natural response, and the particular integral is the forced response. Okay. Free and forced response. In addition, another term which is very often used is that as time proceeds from 0 plus, as t goes to infinity, the complementary function usually dies out. The complementary function of the natural response, which is the response due to the initial conditions of the network, usually die down exponentially, and then we are left with a steady state solution, SSS, steady state solution, which is usually the particular integral but not necessarily so. Okay. The steady state solution is not necessarily the particular integral, although this is what happens in most of the situations. Now let us look at the initial condition problem through a couple of examples. The first example that we take is that of a voltage source V which is switched on at t equal to 0 to a capacitance resistance network CR, and it is given that Vc 0 minus is equal to 0. All right. We are required to find out if this is the current I after the switch is on, that is VUT is switched on in this circuit. What you have to find out is I of 0 plus, which is the initial condition, in addition one is required to find out, let us say the statement of the problem is find I of 0 plus and I prime of 0 plus. Okay. Then there are two ways one can do it. One is from physical conditions. Physically we argue that the capacitor voltage at t equal to 0 minus was 0, and the current does not have an impulse component, and therefore Vc 0 plus must also be 0. That is, at t equal to 0 plus the capacitor acts as a short circuit because it does not drop any voltage, and therefore I of 0 plus must be equal to V by R. I of 0 plus, at 0 plus V, C is a short circuit, so a resistance R is connected, and therefore it must be V by R. This is from the physical conditions. From the physical conditions, however, we cannot find out I prime 0 plus. We have to write the differential equation. The differential equation is VUT equals to, now I write a single loop or mesh or whatever you call it. I write 1 by C integral 0 minus to t I tau d tau plus R I. This is my simple single loop equation. All right. Now from here, from the differential equation, we could find out I of 0 plus, because 0 minus to 0 plus, this integral shall be equal to 0. I of t does not have an impulse component, and therefore I of 0 plus shall be equal to V divided by R. That is all. At 0 plus ut is equal to 1. All right. So we could have found this out from the differential equation also. To find out I prime of 0 plus, that is a more interesting exercise. What we do is we differentiate the equation. Then I get this is equal to 1 by C, this will be simply I t plus R I prime t. Prime stands for differentiation with respect to time. And in this equation, if I put t equal to 0 plus, what does the left hand side become? 0. At 0 plus delta t is 0. this becomes 0 because I of 0 plus is 0. So, this is also 0. Now, V by R. So, it would be V by R C, okay, plus R I prime 0 plus, and therefore I prime 0 plus becomes equal to minus V divided by R squared C. This is the equation. Now, this was not needed for solving the equation. All we needed was I of 0 plus, but this is a matter of curiosity. What is the slope? The initial current is V by R, but how does the current change? You see, you know that the current in this circuit starts from V by R and then goes down exponentially. This is why the slope is negative. The slope at the initial point at t equal to 0 is negative because it decreases and the value is V by R squared by C. The next equation, next problem that we take is a similar problem, but contains a capacitor, the same voltage source V. It contains an inductor L in series with a resistance R, and it is given that IL of 0 minus, if this is I of t, then I of 0 minus is equal to 0. That is, the inductor is initially uncharged, and here also you have to find out I of 0 plus, let us say I prime of 0 plus, and in addition let us say I of infinity, that is the steady state part. Okay. I forgot to mention, what would be the steady state solution here? 0. It is obvious, the current drops exponentially. Okay. Now, here my equation is, I can argue again from physical conditions, physical point of view. Well, from physical considerations, I of 0 minus is 0, the voltage source does not have an impulse, therefore I of 0 plus must also be 0. In other words, at t equal to 0 plus, the inductor acts as an open circuit. So, the initial condition on the current is 0, therefore, the current must start from here. Current versus time, it must start from here, alright. Then, if I want to find out I prime of 0, this is 0, I prime of 0 plus, how does it rise? Okay. Now, can it fall? It may, if V polarity is negative, isn't that right? You must be very careful about polarities. If I write I in this direction and I reverse the polarity of V, then obviously the slope can be negative. But anyway, considering this situation, you have V times u of t is equal to L di dt plus Ri. This is the equation. This is a differential equation, there is no integration in this, and you notice that if you put 0 plus here, then you simply get, if you put t equal to 0 plus, you simply get L V equal to L I prime 0 plus R I of 0 plus, which is 0, and therefore I prime of 0 plus would be equal to V by L. It is a positive quantity, so it must rise like this, and then I of infinity can again be found out from physical considerations or from the differential equation. See, as time proceeds, I of infinity, the inductor acts as a short circuit, and therefore the current must rise to V by R. You can also look at it from the differential equation. At t equal to infinity, di dt, I stabilizes, so di dt is 0, and therefore I must be equal to V by R. So the current rises like this. This is V by R. Okay. The point is, we have found out the initial conditions from either physical considerations or from the differential equation. Yes.
Can you find I of 0 plus from the equation?
From the equation. Oh, can we find I of 0 plus from the equation? Yes. Can someone answer this question? Can we find I of 0 plus from the equation here?
Yes, sir, we can.
Okay, tell me how. At 0 plus, this is V. Okay, this is R I 0 plus. What is d I dt 0 plus? We don't know.
Depends on L.
Pardon me?
Depends on issue. L.
So we know, sir.
Inductance.
How?
So we found I prime 0 plus.
But
No, we want
okay,
I found I prime 0.
that required I 0 plus.
I0 plus.
Okay. Well, it's possible, but let's defer the discussion for a moment. Okay. For an engineer, anything that works is a good solution. Okay. Either from physical consideration, you find out which is the most convenient. While differential equation, it is not convenient. It doesn't give directly. We have to go through some other means. Why go through some other means if you can find out from physical conditions? We take a third example. In the third example, we have a capacitor as well as an inductor. We have a voltage source V, a resistance R1, a capacitor C, a resistance R2 and an inductor L. And the currents are identified, not loop currents but branch currents, let us say I1 and I2. Obviously, this current would be I1 minus I2, the current through the capacitor. Now, we do not have to do anything else, we can simply appeal to the physical conditions and find out initial conditions. For example, I1 0 plus, we of course assume that inductor and capacitor are initially relaxed, that is I2 0 minus is 0 and the Vc 0 minus is 0, we assume that. Then I1 0 plus, what would this be equal to? At t equal to 0 plus, the capacitor is a short and therefore I1 0 plus must be V by R1. What is I2 0 plus? 0, because if this is a short, then no current passes. Okay. And what is I1 of infinity? When it okay, V by R1 plus R2. This is because the inductor behaves like a short circuit and the capacitor is open. All right. So, and what is I2 of infinity? It is the same. Wonderful. We did not have to write the differential equation. We can do that if you so desire, but we did not have to write. Okay. The next question is about steady state solution. We have already found out steady state solution for the previous 3 examples. Okay. Now, there is one situation in which the finding the steady state solution in practice is an extremely important step, and this is when the excitation is sinusoidal. Excitation is either sine of omega 0 t or cosine of omega 0 t. You know, there is a preference for sine in naming it. We could have called it cosinusoidal, but cosinusoidal, if you write cosine, it is cosinusoidal. Okay. But since it involves another 2 letters, co, we go for an economic solution, sinusoidal. Okay. So, by sinusoidal we mean sine as well as cosine. Now, if to a network LLFPB network the excitation is sinusoidal, let us say sine omega 0 t, then you know that the voltages and currents in the networks can be solved by means of phasors. Okay. The sum and substance of phasor analysis is that if the excitation is sinusoidal, then for a linear network the response must also be sinusoidal of the same frequency. The only difference would be that the response would be different in amplitude k, which will depend on the frequency omega, and the response may not be in phase with the excitation. So, there may be a phase difference phi 0 of omega 0. The phase difference and the amplitude both shall depend on the frequency. and we shall, yes.
This amplitude could be a product, or you know, it could be divided by omega, that sort of function, or any way.
Any function, it's simply a general function of omega 0. And to illustrate this, we take a simple example. Let us say we have an I0 sine of omega 0 t, ut of course, and a parallel combination of R and C, and we are required to find out Vt. Okay. Then we simply argue that capital V, the phasor, capital V j omega would be simply I0, the phasor for this is I0 multiplied by the impedance. The impedance is the reciprocal of the admittance, and the admittance is G plus j omega c, which I can write as I0 divided by square root of G squared plus omega squared c squared, and the angle is minus the angle of the numerator minus the angle of the denominator. So, minus tan inverse imaginary part divided by the real part. Do you know this? And therefore, Vt I can write by inspection without solving any differential equation. I can write as I0 divided by square root of G squared plus omega squared c squared. This is my k. Okay, this is my k, and sine of omega 0 t minus, because the phase is minus, tan inverse omega 0 c divided by g. That eases our problem if the excitation is sinusoidal. We will meet after 1 hour.